is Dr. Zonghuan Lu from RPI, Quasi van der Waals epitaxy of copper thin film on monolayer graphene buffer.
Okay. Hello, everyone. My name is Zonghuan Lu. Today, my topic is the Quasi van der Waals epitaxy of copper thin film on monolayer graphene buffer. So actually, Professor Wang and Dr. Shen already talked about the van der Waals epitaxy, and here just a little bit more. The van der Waals epitaxy actually utilizes the weak van der Waals. The force is strong enough to achieve sufficient bonding orientations between the epitaxyof layer and the substrate, but it has, because the weak interaction it has the less bonding strength. So basically, the epitaxy can release the lattice mismatching requirement limitations compared to the epitaxy caused by the covalent bonding and ionic bonding. So the van der Waals epitaxy can form the ultra-thin epitaxial films with even sub-nanometer thickness and has the abrupt interface with very low defect densities. So in this case, the epitaxy requires a substrate substrate to be free of dangling bonds. So in this case, we already talked about the mica, the graphene, and also people use the selenium, tellurium, and hydrogen terminated silicon 111 and the calcium fluoride. There's many materials can achieve the van der Waals epitaxy. And there's on the top of the slides, I show three types of different van der Waals epitaxy. The first one is the 2D materials on 2D. So this is just the 2D materials epitaxy on 2Ds. And the middle one is the 2D materials epitaxy on the surface terminated materials, means there's no dangling bond on the surface. And the last one is called the Quasi van der Waals epitaxy. Basically, it's 3D materials grow on the 2D surfaces. This 3D materials is not necessarily be free of dangling bonds, but still it's just can be on common materials with dangling bonds, but it still can grow on the 2D materials. So today I'll talk about is the copper thin films. Use this Quasi van der Waals epitaxy grow on the graphene. We want to achieve the high quality epitaxial films on graphene to study the electron surface scatterings. Why we choose graphene? Because graphene has some advantages. One is that it has a low density of states, so it can avoid the disturb the copper surface potential, and it can grow low defect density copper films. In this way, it can reduce the diffusive electron surface scattering in the copper film, and we can further reduce the electrical resistivity when we shrink down this copper film thickness down to the deep nanometer range. And the other advantage is that the graphene theoretically is impermeable to most of the molecules, so it can serve as the good barrier for interdiffusion between copper and the surrounding materials. So we first study, investigate different deposition methods, because some of the deposition methods can cause damage to graphene, so we won't be able to achieve the good epitaxys. So in this slide, I show we first use the thermal evaporation to deposit the copper on the graphene buffer, the silicon oxide wafer. This silicon oxide basically is amorphous glass wafers. On the top two images show this is the SEM image of monolayer graphene transferred to a silicon oxide. Basically, it's You can, from the Raman spectrum, you can see it's a very good, pretty good monolayer graphenes with high 2D to G ratio and small D defects, so that this graphene film has a low defect density. There's a little bit bilayer graphene flakes on the surface, but it doesn't affect the general quality of the graphenes. And the bottom one, we deposited like 5 nanometer copper on the graphene, because at this thickness, the copper film is still not continuous. So we can use the Raman microscope to check the graphene if there's any damage, and the spectrum, so that there's negligible defects peak. So meaning that the thermal evaporation method is mild enough so to damage the graphene layer. And we also try the other sputtering. The other method is the spot DC and the RF sputtering, because this one is the sputtering method is a pretty popular method to deposit the metal materials. In this case, we know that normally sputtering method will damage the graphene in the normal ways. And in this setup, we use the flip sputtering method, in the meaning that we mount the graphene in a way that the graphene is face away from the copper flakes. So the deposition is mainly caused by the random scattering of the atoms in the system. But the top two pictures show that the result of the DC sputtering of copper, 5 nanometer copper on the graphene, and the Raman spectrum, so that there's a severe damage. Basically, the 2D and G peak disappeared, and it's only a big hump of D peak. Basically, this is a spectrum like amorphous carbons after the depositions. The bottom one is we use the RF sputtering. Yes, the 2D and G peak is preserved, but you can see that compared to thermal evaporations, the D peak is quite significant. So this means that the sputtering method, even with the flip sputtering setups, we still get the severe damage to graphene. So in the following works, we use the thermal evaporation to achieve the copper depositions. We also investigate the temperature effects, at which temperature we're getting good epitaxyof deposition of copper on the graphene surface. And this basically is the data is, one is the SEM image of the 20 nanometer copper films. And the following is the electron backscattering result. And from the inverse pole figure, we can see at the Z direction, we can see that the outer plane orientation for this copper film is mainly is 111. But there's some areas also have the 001 orientations of the plane. And the copper 111 pole figure shows that basically it's a polycrystalline structure of this film growing at the 150 degrees C. But there's a little bit the preference orientation. You can see there's weak, 6 weak 111 poles, but there's large orientation dispersed in the chi direction, also in the azimuthal directions. So at this temperature, at the bottom is the EBSD IPF maps. It's showing the spatial orientation dispersion, showing the locations where the orientation is aligned to specific directions. For example, the blue color is the 111, the location where outer plane is 111, and the red color location is outer plane orientation is 001 direction. So based on the EBSD data, we can see that the quality of the graphene at this temperature is not very good. So we increase temperature to 250 degrees C. In this case, we use the bare silicon substrate as control and comparison, and on the top is the 100 nanometer copper film grow on the silicon substrate. So like if you can see this copper 111 porphyry is basically is purely polycrystalline structures, meaning that it's copper grow on the silicon substrate without graphene is purely the quality is not good. So the bottom one is so the result of copper grow on the single crystal monolayer graphene. We can see that we have for the XRD theta to theta scan and we can see that we have a strong copper 111 peak, and this is the only peak in the theta to theta scan. For the 5 scan of copper 111, we can see that there's 6 strong peaks along the azimuthal directions. The corresponding copper 111 porphyry, we can see that there's a 6 sharp strong poles of copper 111. The copper is a cubic crystal structure with 3-fold symmetry. And here we have 6 poles, meaning that there's twin domains exist in this same copper films. The AFM scan of this copper film, and also here the accompanied with the SEM image, so that the film is not very smooth. We calculate the surface roughness around 19 nanometers, but it looks like we can achieve the epitaxy of copper on the graphene in this case. The EBSD, the IPF mapping, so that generally in the outer plane Z direction it's 111. There's a little bit different colors, I think, with different orientation. I think it's because they're caused by the impurities on the graphene surface, such as the residues from transfer process, also the wrinkle and the defects. So we also we also want to know if there's a substrate defect. So we grow the 100 nanometer copper on the quartz 001 substrate, because crystalline silicon oxide substrate. And basically, we can see that the copper directly grow on the quartz substrate is like a weak fiber structure. But after we put the graphene on it, the result is similar to the one in the previous slides. It's there's 6 strong copper peaks with 6 poles, and oh, by the way, I mentioned the full width half maximum of this 6-5 copper 111 peak in the 5 scan is around 9 degrees. This is not very small. So it's in this slide, we can see that the crystallinity of the substrate, silicon oxide substrate, does not have much effects on the copper epitaxy on graphenes, meaning that the graphene has a screen effect, pretty good screen effects to block the silicon oxide substrate interactions. So this slide, we saw that we also grow the copper films on the commercial polycrystalline graphenes. We want to see if the copper crystal orientation is follow the graphene orientation or not. So this, Yuxiang already talked about actually this commercial graphene in his presentations. Basically, it has main domains also had 30 degrees, secondary domain, and also possibly third degree domains rotated like 30 degrees, 30 degrees. So when we grow the copper on these films, we also can see that the copper thin films form different crystal domains, and it's 15 or 30 degrees rotated from its main domains. So it basically is consistent with the graphene orientations. And interestingly, on the commercial polycrystalline graphenes, the surface morphology of the copper is worse than the single crystal grow on single crystal graphenes. And the EBSD maps showing that the out of plane orientation basically is 101, but in plane, the green color region is 101. It's 101, and those purple regions actually is the 101 direction, so they have the 30 degrees rotations. So based on those experiment result, we plot the schematic of the copper graphene epitaxy relationship. It's 111 direction, out of plane direction of copper aligned to the graphene 001 planes, and the in-plane orientation is copper 211 directions aligned to the 10 -10 direction of graphenes. Also, this we also run a geometrical superlattice matching model to try to confirm our result. This model actually is comparing pairs of superlattice. One is in the copper, the other is in the graphene. We try to find a pair of superlattice which has the minimum area difference. So it's tell us that the minimum mismatch, and which is systematic energy favorable in this case, and it's most likely happened in the epitaxy process. And the results showed us that the lattice vector of copper and graphene are match at when the rotation angle is 0 degrees, meaning that they have the parallel alignment to each other, which is consistent with our experimental results. So our future work, we need to improve the copper film roughness, because from the AFM image we can see that the copper roughness around 19 nanometers, which is very rough. It's preventing us from growing ultra thin copper film for the electrical studies. So because the graphene has very low wettabilities, so copper tend to form the 3D structure on the graphene. So the other things that we still have the large in-plane orientation dispersion, so meaning that there's exists small angle crystal domains, which is not very good for the electron scatter, as will cause the electron scattering. So we need to reduce these dispersions and get better quality copper films. That's the future work we're going to do. So we thank RPI clean room staff for the help of fabrication and the characterization of this copper film. Also, this project is supported RPI Focus Center through NY's NESTA contract. Yes, that's it. Any questions?
Open for questions.